Today we have the pleasure of welcoming Patricia Pinto, who is professor at the Faculty of Economics of University of Algarve, where she teaches data analysis, statistics, and econometrics, and coordinates the Research Center for Tourism, Sustainability, and Well-being. Patricia also coordinates the PhD program and is a member of the board of the PhD in Tourism and of the Master in Marketing Management. She participates in different projects and currently coordinates a special project on residents' attitudes and behavior towards sustainable tourism development in the Algarve, where she is from. Today, Patricia will talk to us about an application of structural equation modeling in tourism management research. Patricia, welcome. Thank you very much for having accepted our invitation, and the floor is yours. Thank you.
Good morning. Thank you very much, Paula, for your kind words, and thanks to the Faculty of Economics of the University of Oporto, also for this invitation. It's my pleasure being here. I will share my screen. Just 1 minute. I hope that you are seeing now my PowerPoint and also hearing me well. Can you please confirm, please?
Yes.
Okay, thank you very much. So thanks to Paula Brito, thanks also to the colleague Maria Eduarda Silva. My seminar is about structural equation modeling in tourism management research. I really hope to give some insights about the methods, and I hope that you enjoy and hopefully want to apply it in your future research. So this is the outline of our seminar. I will start with the objective, the main characteristics of the methods. Then I will talk about the different types of Cm models we can have. Then we will enter a little bit in the methods, and I will talk about the variables that will be using, the symbols, the parameters we have to estimate, and the equations implied in the model. Of course, Cm has assumptions. We need to see how to specify the models, and of course, the estimation issues, and very important, how to validate our model. We need to know how can we decide that we have a good model and we can advance with our research. And finally, I will show an application in tourism management research, because as Paula was saying, I'm now coordinating a research center in tourism, so my research is mainly applied to the tourism sector, and also because I live in the Algarve, and of course, tourism has the important that everyone knows. So, starting with the objective in main characteristics, I need to say that this method is used to estimate relationships that can be direct or indirect between latent variables, and between these latent variables and a set of observed variables that are also called indicators. So latent variables are strange variables. They are abstract concepts that we cannot measure with a single item. So we have a set of items, of indicators to measure these latent variables. The observed variables or indicators are really that items that we collect data for them, for example, using a questionnaire, and that we will use to measure our latent variables. So this is a typical model that we can estimate and validate using structural equation modeling that we used to call Cm from structural equation modeling. So we have here 4 latent variables: destination loyalty, overall satisfaction, destination image, attribute satisfaction. You can find here the paper where this model was tested. We can see that we have here some research hypotheses. So the method will test the relationships between these variables, latent variables, and also to do that, we need to have a list of indicators, items, to measure each of these constructs. And the model will tell me also if my items are good measures of each of these 4 latent variables. So the origins of the method. This method is not new. It became mainly from 3 research fields. Path analysis in the beginning of last century. In path analysis, researchers were concerned in expressing models, simultaneous equation models, by using a picture, a path diagram, and also how to express these relationships between the variables using the concept of covariance that today is the basis of covariance-based Cm, of PLS, of covariance-based Cm, which will be the approach that we are going to use. We also had the measurement models that were being used in the psychology. People from the psychology were concerned about measuring concepts such as intelligence. How can I measure intelligence? Of course, intelligence cannot be measured with a single measure, with a single item. I need a battery of indicators, of variables that I can observe, that I can measure, to see if, to understand to what extent someone is intelligent. So also psychology had here an important role with the measurement models. And finally, in econometrics, of course, using simultaneous equation models involving quantitative variables and advancing in estimation methods and ways of assessing that models. So from the mix of these 3 types of analysis, the method developed, but the most important here was in this moment in the 70s of last century, with the work of these 3 authors. We invented an important software, the Residual software, linear structural relationships that really allowed to implement the method. And since then, we can find numerous applications of SAM in all, I would say, in all fields of knowledge. If we check a journal, an important scientific journal, it is very likely that you will find some nice papers involving structural equation models. Well, today we have other software available. In my university, we have AMOS. AMOS is strictly related with SPSS. It works with data from SPSS, and because we also have SPSS available to all students, it is the software that we mainly use. But you have also other software that can be applied to run SAM models. Okay, statistically speaking, we can say that SAM models is a dependence technique because, as we will see, the dependent latent variables can be expressed as regression equations, but it can also be seen as an interdependence technique because the way we link the indicators to the constructs it relies a lot in what we know about exploratory factor analysis. So it is a 2nd generation data analysis method because it relies on methods that were invented before, as we saw. It has this interesting characteristic of combining an econometric perspective because we want to understand the behavior of the dependent latent variables, but mixing with a psychometric perspective because we also want to understand to what extent our latent variables are being adequately measured by the indicators or observed variables. This is a great advantage of the method. It allows to estimate very complex models, work with different type of variables, include in the model different type of effects between variables, direct effects, indirect effects, total effects, moderations, mediations. So we can do a lot with this type of models. It is really very flexible, and it allows us to have very interesting and deep studies using the method. So, advancing, and let's now see the topic 2, typologies of Cm models. We have two very important Cm models. The first one is what we call the confirmatory factor analysis model. Here we are concerned only with the measurement of our latent variables. So the idea is we have latent variables, we have the indicators, and we want to see, to confirm if latent variables are being adequately measured by the indicators. So the focus is on the measurement of the latent variables. But we can also have the hybrid model or the complete model. So here we have the previous concern of confirmatory factor analysis model, because we also want to see how the latent variables are being measured, if they are being measured properly with our indicators, but we have a more ambitious objective because we also want to test the relationships between the variables. Well, what I have here is an example of a confirmatory factor analysis model. See that we have two latent variables, customer delights and positive word of mouth. They are represented by the ellipses that we have here. And we have the indicators, 3 indicators for each latent variable, represented by the rectangles. And we are saying that there is a covariance between the latent variables. So we are not saying that this variable is related with this one. There is a direct relationship. We are saying that there are some correlations, some covariances. So here the focus is not testing relationships between the variables, it's just trying to confirm if these items, these indicators are measuring in the proper way our latent variables. So this is a confirmatory factor analysis model. But I can have also the hybrid or the complete model. Here I have the objective of estimating relationships between the latent variables, and the relationships between them is what we call the structural model. And we have, of course, we have latent variables and the relationships with their indicators. So we have the measurement model, and the structural and the measurement model will be estimated at the same time, simultaneously. So this is an example from this journal, the European Management Journal. I found this model interesting. It is about trying to explain what makes someone want to quit from a company. So based on this model, the intention to quit depends on job satisfaction, to organizational commitment, to what extent we feel we are in the company, that the company is supporting us. Also the perception about distributive justice, to what extent we feel that in the company, those doing the same will be rewarded in the same way or will be earning the same amount, something like that. And this is also very interesting. It depends also on the idea we have about the leadership of the company. So this is an hybrid model because we have relationships between the variables expressed here with the arrows and the hypotheses. And of course, I'm not showing here, but we have in the paper the indicators, a list of indicators that are being used to measure each of them. And the model will be run also to test if these indicators are adequate measures of the latent variables. Advancing 2.3, variables in symbols, parameters, and equations. So the variables in Cm can be divided into two groups. We have the latent and we have the observed, and each of them can be dependent or independent in the model. It depends if they are being explained by other variables. In that case, they will be dependent, or if they are explaining other latent variables, in that case, it will be independent or exogenous. So they can be arranged in this way. Using some Greek symbols as the method was invented using the Israel language, we can represent the dependent latent variables in this way: eta1, eta2, eta_n. The independent latent variables, xi1, xi2, xin. The observed dependent variables, y1, y2, yp, and the observed independent variables, x1, x2, xk. So the symbols that we are going to use, we have the ellipses for the latent variables or the errors. We have the rectangles or squares for the observed variables. We have straight arrows for the relationships between the latent variables, and we have curvilinear arrows to represent the covariances. So this is an example of a model totally represented with the Greek notation. You see that I have here some dependent latent variables, which is rule ambiguity, eta1, and job satisfaction, eta2, and evaluation performance, eta3. They are dependent. They are being explained by other latent variables in the model. But we have also some independent latent variables as job knowledge. See that job knowledge is not being explained by other variables, so it is independent, psi1. The same applies to organizational support, psi2, because it is not being explained by other variables. So what we have the indicators, you see y8, y9, y10, the symbol y, when the latent variable is dependent, and we have the axis, x2, x3, when the latent variable is independent. So we have more. We have the relationships between the latent variables will be the path coefficients. We have here also the relationships between the latent variables and the indicators, which will be the loadings that we also want to estimate. And we have the errors, the measurement errors. Also see that for the latent dependent variables, we have here the latent error, only for the latent dependent variables. These happen here, here, and here, okay? So this is a full model, totally represented with the Greek language. Of course, that if I'm going to use, for example, Amos to estimate my model, I don't need to be concerned with these Greek letters. I just need to write the name of my variables, and then latent variables. I need to draw the model, and I have to have in my SPSS file the indicators that I can give the name that is adequate for me. I can it is not necessary that the name is x1, x2, x3. It can be the name, really name of the indicator. Well, so the parameters I want to estimate. I want to estimate relationships between the latent variables in the structural model. I want to estimate the loadings of the measurement model, the links between the latent variables and the indicators. And the method will also estimate some important covariances between some parts of my model, the independent latent variables, the dependent latent errors, the measurement errors of the dependent indicators, and the measurement errors of the independent indicators, which means that when I run the algorithm, what happens is I will have the most important results for me, which will be the links between the latent variables and the links between them and the indicators. This is what I really need. But more than that, I will also have these results that will be used to compute some measures that are necessary to evaluate my model in the second phase. Okay, the equations. So this is a general equation for the structural model, the general equation for the measurement model for the dependent latent variables, and the general equation for the measurement model for the independent latent variables. Usually we don't see the equations in empirical papers. It is not easy to find that, but I could see that in this paper we have all the equations. It was a paper published in the European Journal of Operational Research. And I can see that we can have there the equations for the structural model. We have here the latent dependent variables. We have an independent latent variable, and we can see how they are related. So the picture the PET diagram was converted into equations. You can see also the errors of the model and the coefficients that you want to estimate. You see the PET coefficients here, relationships between the latent dependent variables and relationships between them and the independent latent variable. And also the measurement model, for the dependent latent variables that is now here expressed, and also the measurement model for the independent latent variables. I used to say to my students that don't be very concerned about this unless you are doing a PhD in quantitative methods or in statistics, because if you are doing something in management or economics, you don't need to be very concerned about the equations. Of course, it is important that you understand what is being doing by the methods. But if you have software, for example, as Amos, you just need to draw your model and you will have your results. But it is important to know that what is being estimated, and what is being estimated is really these coefficients that we have here, the PET coefficients and the loadings, more that covariances between some measurement errors that we saw before. Okay, SEM has some assumptions. It requires a multivariate normality of the indicators. However, advances of the method show that we can also use, there are some estimation methods that can be applied when these don't happen, and usually, or it can happen that our data are not so well behaved as we would like, and we need to deal with that. It requires metric dependent variables. It assumes that we have linear relationships between the variables, that the constructs are unidimensional. We need complete data sets. Data, sorry, we have here, it's not data, it's data set. So which means that we have missing data. We need to deal first with that to resolve the situation using the methods we have available to deal with missing data, because to run the model, we need our full data sets, and we need an adequate sample size. Okay, about the sample size. This is a very important issue in SEM. So the big question is, how much is enough? We have some rules about that. Authors have been proposed some guidelines. For example, these authors was saying that 10 cases for each indicator would be enough. This author is more demanding. It talks about 15 cases for each indicator. Some authors propose a minimum of cases for parameter to be estimated, as this one, 5. This is more demanding, 10 cases. Other authors propose an absolute minimum sample size. So you see that there is not a consensus about this. There is not a magical number about this. The most important is to what extent is our sample representative of the population that we are trying to study and to test relationships with our model. So nowadays, I believe that this is the most important, and you have here the source. I believe that this summarizes very well what is nowadays required to researchers, is that the more heterogeneous the population, the larger the sample size needed to achieve an acceptance sampling error. If basic sampling theory guidelines are not considered, questionable results are produced, of course. So to compute the required sample size, researchers should rely on power analysis that consider the model structure, namely the complexity of the model, how many latent variables we have, how many indicators we have, and also the significance level that we want to have in our analysis and expected effect size. There are tables that allow us to, based on these values, to give us the adequate sample size, and even automatic calculators that we can find easily in the internet to do that. So if I can suggest something, I would suggest this power analysis to have for a specific case, considering our model, considering our significance level, try to find the adequate sample size in this situation. Advancing with the specification in SAM. Well, so we need to read, to try to explore, to understand what can be the relationships among our latent variables. Usually, these require deep literature review. We cannot go there and just try to link variables, because if you do that, of course, that will be an empirical model. We can run the model, but very hardly, I would say that it will be impossible to publish that in a good journal. Everything needs to be very well supported. So what are the relationships between the variables? What are the relationships between the latent variables and the observed variables? Once again, I suggest a deep analysis of what can be the indicators of each latent variable. Do I have validated scales? In what papers that constructs were used, and were used using what items? That is where that deep reflection is really very important if we want to have good results for our model. Do we want to confirm a theory? Do we want to compare alternative models? This can be done using covariance-based SAM. So it is very important, a solid background theory. This is a necessary condition, I would say, to propose a nice model, to propose a nice measurement model, and then to have to increase the likelihood of having good results, and of course, consequently, be able to publish our article, if it is our thesis, to have good results for our thesis. Well, this is an example of a model. Here, the objective of the authors was just testing relationships between variables, testing a theory, and they want to test what explains self-esteem. Okay, self-esteem is a function in this model of global physical self-concept, which depends on our idea of our body fat, our appearance, and our strength. So the model was specified to confirm a theory. Okay, you have here the link for the paper. You can find details about this model. Here it is an example of specification a model to compare alternative models. So this is a paper published in the Martin field, and the authors propose relationships between brand dimensions. You see brand consciousness, brand preference, brand sensitivity, brand importance, and they are applying structural equation modeling to test the model. But they are not sure about what is the best path between the dimensions. So they have here different alternatives, and they will test each model, and so they will compare these results. They will compare the overall fit of the models to decide what is the best model. So the idea is comparing models in order to select what can be the best one. Well, but we can also use SAM to test direct effects. This is the basic, but we can also test indirect effects. See that variable M here, it is indirectly affecting the relationship between X and Y. So I can test the relationship between X and Y, but also can test the indirect effect using the variable M. So hypotheses involving indirect effects can also be tested in SAM. We can find nowadays some papers, and that really enriches my analysis, testing mediation. Mediation has to do with indirect effects. For example, I can test, I will have a partial mediation when I have something like this. The relationship between X and Y is significant, but also the indirect relationship is significant. In that case, I will say that I have a partial mediation. M is partially mediating the relationship between X and Y. But I can have also a full mediation. So I have full mediation when the direct relationship is not significant, however, the indirect relationship is. So this is one way of improving my analysis and making my models more interesting. Also testing mediation. Still regarding specification, I can also test moderation. For example, I have this model, 3 latent variables: adaptive behavior, costume effects, custom light that affects positive word of mouth. However, imagine that I have a strong theory supporting that this relationship also depends on what extent someone is more friendly or less friendly, okay? So the level of friendliness will affect this relationship. So I can test the moderating effect of friendliness in this relationship. This can be applied also with categorical variables. For example, imagine gender. Suppose that I have reasons to assume that this relationship is stronger among women than among men. So I really have, I can also improve my models and in my analysis becoming more interesting, considering the moderating effects. Also, I can test high order constructs in SAM. For example, sometimes you have latent variables that are so abstract, so latent, that are so latent that I cannot have unique indicators to measure these variables. So the variable is, the indicators are other latent variables. And for these latent variables here I have indicators. So, but for this one, I don't have indicators. So it is measured by other latent variables. This is what we call an hierarchical model. This can also be used in SAM. And once again, because our models can become more interesting if we can do this type of analysis. Of course, everything needs to be justified. Just doing that and trying to do that because we want to make our models more complex, if we cannot justify the reason for doing that, it is better to keep them simple. But we really need, we really can do this using a structural equation model. Estimation in SAM. Well, so here the idea is this one. So we have our data, and the approach I'm going to talk is covariance-based SAM. So I have the relationships between my indicators expressed through the covariances between the observed indicators, and I have my model. So the draw I did with the relationships between my variables. So I want to find the parameters that best approximate my model to my data. Okay, that is the idea in covariance-based SAM. So in covariance-based SAM, the focus is on the covariances between the variables. And the idea is to estimate the parameters by minimizing the differences between the observed covariances among all pairs of indicators and the covariates that are implicit in my model. Considering, of course, the specification I did before. So I will have the matrix of variance and covariances that are represented by X, and I will have the implicit variance covariance matrix given by my model. So that can be, it can be proved that it can be represented this way. When here in the middle, I have all the matrices of parameters I need to estimate, namely the most important, those included, those related with the structural model, and those related with the measurement model. And what is going to be, the big question is this one. What are the estimates for the parameters that make these metrics as similar as possible of my data? And my data will be the observed variance covariance matrix between my indicators. What are the parameters that best approximate the two matrices? So what we are going to have is a discrepancy function between the two metrics, and we want to minimize that discrepancy function. That function will have different forms that will depend on the estimation method. The maximum likelihood method is the most often used method. As I say here, it leads to estimates from our parameters, maximizing the likelihood that the covariance matrix X is drawn from a population in which the model implicit covariance matrix is valid. for example, in AMOS, it is the method that is chosen by default. The question is that it really produces nice results, consistent estimates for the parameters, assuming that really our indicators, they follow a multivariate normal distribution. And sometimes here we have some difficulty. But of course, we need to test. And there are some studies that show that if we don't have big departures from the normality, the method still works well. So usually I would say that if you check some papers using covariance-based SEM, you will see that most of them are using maximum likelihood estimation. There are other methods. One of the methods is this one, the weighted least square method. It is an asymptotically distribution free. It is not sensitive to normality. So when our data is not normal, it is an option. It produces unbiased estimates for the parameters. So we are happy with that, but it really requires big samples, and that can be a problem in some situations because we really want that big samples, but our data is what it is, and sometimes we can have that difficulty here. Well, validation in SEM. Let us imagine that we have our model, everything is well supported in theory. We check normality and we have normality, or at least we don't have significant departures from normality. So we will run our model, we will have the results. So we will really want to know if we have a good model. And then to test our hypothesis into and writing our paper. So what should we check in order to decide that we have a good model? So we need to check an overall assessment of the model, and we have different indexes for that objective. Then we need to check the measurement model. Is it okay? Are we really measuring in the proper way our latent variables? And then to check our structural model and really make conclusions about our research hypothesis. This is a nice paper that is free online that really explains all the measures very well, and also the estimation methods if you wish to see more about the details about the estimation method. It is not very recent, but is really very pedagogical and explains everything very well. Well, about the overall model, overall assessment. So we have absolute fit indexes. Basically what they do is to analyze the degree of closeness between that two matrices, to what extent they are close, and we want them there as close as possible. We have the incremental fit indexes. What they do is to compare our model with the worst model that we can have, which is called the independence model. It is a model where anything is related to anything. So a model without any significant relationship. So the idea is to compare our model with the worst model. And finally, we have what we call the Persimmonious fit indexes. They will compare the fit of our model, but in a relative way, because taking into consideration the number of parameters that we need to estimate to run the model. Well, absolute fit indexes, what we have. The most important, the basic, is the chi-square goodness of fit test. It is a test where the null hypothesis is that the two metrics are equal. Of course, we want not to reject that hypothesis, so which means that we would like to have a chi-square low and not significant. A p-value for this test higher than 0.05 if we are working with 0.05 significance level. Unfortunately, this test is very sensitive to sample size, which means that it tends to reject all the models in the big samples that we need to run the model. Which are big samples. So usually in big samples, even if our model is a good model, these tests used to come with a p-value close to 0. Okay, so we cannot rely our decisions about the model based only on these tests. We need to do it because it will test the basic of the model, which is the proximity between the two matrices, but we cannot rely only on the test. So we have other measures as the goodness of fit index. What it does is it tells us the relative amount of the observed variances and covariances, which are predicted from our model. It ranges from 0 to 1. We want big values. Higher than 0.9 is acceptable. If higher, 0.95, for example, would be better. But 0.9 is already a good number. We have also the adjusted goodness of fit index. It adjusts the previous results considering the model complexity. Also ranges from 0 to 1, and we also want big values, but here 0.85 is already a good number. More indexes of absolute fit, the root mean square residual of approximation. Here it's the square root of the estimated discrepancy due to the approximation, considering the degrees of freedom. Here I want low values. Values lower than 0.08 are good values. We have the root mean square residual index. It is an overall badness of fit measure. So I want a value close to 0. The guidelines is that if my RMR is lower than 0.05, that would be very, very good. Incremental fit index. Do you remember to what extent my model is better than the independence model, the worst model I can have? So I have different measures for these invented by different authors. They will be all, for example, in Amos in the output, and they all range from 0 to 1, and I want big values, desirably higher than 0.95, but if they are higher than 0.9, that is okay. Parsimonious fit index. We have the parsimonious norm fit index. It is a modification of the norm fit index, but considering the degrees of freedom. It also ranges from 0 to 1, and also values higher than 0.9 are nice values, and the norm chi-square, which is simple, the result from the chi-square statistics divided by the number of degrees of freedom of my model, and values ranging from 1 to 5 are desirable values. Well, let us see that, let's suppose that we do this first analysis and the model is okay in most of the measures. Then we will check the measurement model assessment. This is very important because I really need that my latent variables are being adequately measured by my indicators. This can be a good reason for my paper being rejected if that is not happening. Because see, how can I test relationships between constructs that are not being well measured? So sometimes students, they stay very concerned because some of the hypotheses in the structural model are not being confirmed. I say that that is not a problem if some of the hypotheses are rejected. I really believe that will enrich my analysis if some of the hypotheses are not supported, because I can improve my discussion. But if the measurement model is not okay, that can be really a problem. So I really recommend deep readings about latent variables and try to have indicators well chosen. If I need to do interviews, I will do interviews, but it is really big, very important, a nice support in the nice measurement model. So how can I check the measurement model? The most important is to test reliability. To what extent the observed variables chosen to measure latent variable are actually measuring the same concept, but also the validity. To what extent they are measuring the concept that I think they are measuring, and not a different concept. See, I believe that this picture really shows this well. For example, here I have these points representing the indicators, the observed variables. They are really measuring the same, so they are reliable. But they are not measuring my targets, so they are not valid. Okay, they are reliable. They are measuring the same thing, but not what I think they are measuring. Here, they are reliable. They are measuring the same idea, and they are measuring my targets. Here, they are not measuring the same thing. The points are dispersed. They are measuring different things, and of course, they are not measuring what I want them to measure. So they are not valid, not reliable. What I want is this. I want reliability and validity in my measurement model. So what should I check? I should check the individual reliability of the indicators. So I need to check the loadings. Desirably, they should be higher than 0.7. This is discussable, the Cronbach alpha. Some authors say that in SEM you should not use the Cronbach alpha because the Cronbach alpha assumes that the loadings have the same weight. And this is not happening in the model. So, however, if you don't present the Cronbach alpha in your paper, the reviewers of your paper will ask you. So, usually I put information about the Cronbach because this is not consensual. So it is everyone knows this measure. It's a measure of joint correlation between the observed variables. We can also have the composite reliability coefficient. The objective is the same of the Cronbach alpha, but it has this particularity of considering the different weights of the loadings in their relationship with the latent variable. So in AMOS, for example, this is not computed automatically. We need to compute it. Here we have the formula. And the objective, the idea is that we have for the alpha and also for the composite reliability coefficient a value of at least 0.7. Well, validity. We have some measures of validity, namely convergent validity. The idea is to what extent the indicators actually measure the latent variable. How to evaluate, we can check the loadings once again. We want that the loadings, they are high than 0.7 desirably, and they are statistically significant with a p-value of 0 in preference. So each indicator should load significantly on the corresponding latent variable. We also need to check the average variance extracted. And here sometimes we have problems because we really need that this value is higher than 0.5, because if it is not, we will have problems with the reviewers of our paper. And this happens mainly when some of our loadings are very low. For example, if I have loadings in my measurement model for a construct and they are below 0.6 or even 0.55, the consequence is that my AVA will be lower than 0.5, and that is a problem. So I need sometimes to delete some items in order to increase the average variance extracted. It is the average of the R squares for the construct indicators. It gives us an idea of the variance of the latent variables that it captures on average from that indicators. It is not computed automatically by the software. We also need to compute, but it is very easy to compute. There are automatic calculators, or we can have the formula in Excel, for example, and do the calculation. It's very easy. For discriminant validity, this is also very important. To what extent our latent variables are really measuring different concepts. We have how to evaluate. We need to check the correlations between the constructs. This will not be in the output. So what is recommended is that we compute composite variables for each construct, average their indicators, for example, in SPSS, and also and then do the correlations between their proxies, I would say, of the latent variables. They should not exceed 0.7. It is a recommended. So this means that the construct, of course, they have some correlation, but they are not too correlated, because if they are too correlated, that can mean that they are not different concepts, but instead they are measuring the same. And we don't want that. We want that each concept is unidimensional. So it is measuring one idea, and the two different latent variables are measuring two different ideas. We also have this criteria, which is very important, the Fornell and Lacker criterion. Here the idea is to compare the variance extracted by the constructs indicated, which is given by the AVE, and compare it with the variance that each construct shares with the other constructs of the model. So a practical rule is that the square roots of the construct's AVE should exceed the correlations that we computed before between the construct and the other constructs. Then let's assume that we were okay with our measurement model. We have individual reliability, we have construct reliability, we have convergent validity, we have discriminant validity. So we can go on and assess our structural model, test our hypothesis. So here our highs should go to the standardized path coefficients, the relationships between the latent variables. We are interested in checking if they have the right signal, because I'm imagining that I'm testing if variable A is related with variable B positively. So I want a positive coefficient, but I also want that the coefficient is significant. So imagine that it is significant, but it has a negative, the coefficient is negative. So in that case, I will reject my hypothesis, okay? So I need to check both. How to evaluate? I will look to the path coefficients, the signal, the t-values, the p-values, everything will be in the output. It is also usual to see authors indicating R-squares for the latent dependent variables. They will be in the output. They have the same meaning, of course, of the R-squares in multiple regression. The proportion of the variability of the latent variable that is explained by the corresponding model. That is the idea. Of course, in these models, we are explaining very often human behavior, so we cannot expect R-squares very high, but we will be happy if we have an R-square of 0.5, 0.6 in our latent variables, mainly in the last ones that are main ones that we are trying to explain. Well, I'm almost finishing. This is an application in tourism management research. It is a paper that was published in 2017 with one of our PhD students, Manuel Lector Ribeiro, which is now a senior lecturer in Surrey University. I was one of the supervisors. It is about the relationship between residents' attitudes towards tourism and the residents' adoption of pro-tourism behaviors. So it was a study did in Cape Verde Islands, because Manuel Lector is from that country. So this is the model. We have here rectangles, but these are latent variables. And we have the relationships between the variables that are indicated in my model. So we collected data from 418 residents in the country. And we have, based on what, of course, these hypotheses were all very well supported in the literature, in previous literature. Let me tell you that the journal, Tourism Management, is a top journal in the tourism field. So papers need to be very, very well founded, well supported in the literature. I can have a very nice data analysis and everything is very detailed regarding the results of estimating the model and so on. But if the paper is not innovative enough, it will not be published, or if everything is not very well supported. So I used to say to my students that the most important is really to propose, to be able to propose innovative and strong model, everything very well supported. And also this, which is, see that I have here six latent variables. So I need to have my items, my indicators to measure each latent variable. Here I have scientists that I was assessing with the Likert scale from 1 to 5. So these items were also extracted from the literature review. So this for the three first latent variables, and then for the next latent variables, I have here the Cronbach alpha. So more constructs and indicators. So what we did first, the overall assessment analysis. These results are some results important. See that the p-value for the chi-square test, it was 0. This result is rejecting my model. It is rejecting that the two metrics, the covariance matrix between the observed indicators and the covariance matrix implied by the model, they are not equal. This is what this result is telling me. But I also know that for samples as for hundreds as we have, this would be the expected result, because usually in models, in complex models with big samples, this happens. So we relied our analysis in the other indexes. For example, see that here, this result that should be lower than 5, it was 1.45. These two indexes that should be desirably higher than 0.9, or even better if they are higher than 0.95, we had that good results. This result here should be lower than 0.08, and it was 0.035. This result should be lower than 0.05, and it was 0.035. So we were happy with these results. So we advanced for the measurement model, which means that we analyzed the loadings, the relationships between the indicators and latent variables, see that they were all higher than 0.5. We assessed the composite reliability, the values were higher than 0.7, and also the AVE all higher than 0.5. And we did that also for the other 3 latent variables. I don't have here the results, but the idea is the same. Then we assess discriminant validity. So we see that we have here the latent variables that we computed in SPSS by averaging the items in each latent variable. We see that we can have here the correlations. We have here the values. We don't have values. We have here this 0.74, but it is not excessive. And the Fornal-Lacker criteria was being applied because the squared roots of the AVEs here in bold were higher than the values that we have in the corresponding column. So we were happy about discriminant validity too. So then we checked the structural model, which means we have our relationships between the latent variables. They are here. We have our hypothesis. We have the PET coefficients, the t-statistics, and we have here the p-values with the symbols here. We can see that some of the relationships some of the PET coefficients were not significant, which means that not all our hypotheses were supported. We have two hypotheses that were not supported, and the other hypotheses were supported. Here in this paper, we also computed some indirect effects and total effects. Okay, then based on that, we made our conclusions. So, and that's all. Thank you very much. Muito obrigada. I hope you could understand. I know I was everything very fast, but it was my intention to give you an overview about the method, what can be done, what are the most important concerns about specification, the most frequently used estimation methods, how to evaluate the model, and an example. Of course, each of these topics could be a research seminar. There are here some topics that could be research seminars. For example, how to deal with the hierarchical models, how to deal with the moderation. It depends if the moderator is quantitative or if it is categorical. So we have different ways of exploring more these models. So